In this video, we're going to take a short look at the energy content of a system and talk about some ways in which that energy can change, and then look at the energy equation, which we find in a lot of different problems, and see if we can relate the two ideas, the idea to the math, that is. So the red circle here indicates a system. It's a collection of things that I care about. It's user definable, right? I set the boundaries of my system by choosing what to put into it. But as soon as I do that, what I've done is I've enclosed some sort of energy content. And that energy can appear as either kinetic energy, what I've called Ke, or potential energy, Pe. Of course, kinetic energy is the energy of motion. Potential energy can take a lot of different forms. There's gravitational potential energy, there's spring potential energy. Those are the two forms I deal with most in my physics classes. But in other classes, you might run across chemical potential energy, nuclear potential energy associated with certain bonds. There's lots of different forms of potential energy. But the idea is, if I sum it all up, I get some amount, and that amount is not going to change as long as my system is isolated, as long as nothing gets in or out. Now, within the system, things can change from kinetic to potential and back again, and they do frequently. Think of dropping a ball off a building. Initially, the energy of the ball is all potential, and then as you drop it, it starts to move and pick up speed, and the energy goes over into kinetic energy until at the bottom of the building, it's all kinetic and no potential. So it can go back and forth easily, but the amount doesn't change. Now, what if I want to change the amount of energy in my system? Well, to do that, I have to put energy into it or take it out. In other words, I have to let energy cross the boundary of my system. I either input some or take some out. That is done with a process called work. So work represents energy that's crossing the boundary of my system. It can either go into my system to increase the total energy of my system. I'm going to call that positive work. It can come out of the system. It can decrease the total energy of my system. I'll call that negative work. Now, the energy that goes into or comes out has to appear or come from either the kinetic or potential or both of my system, right? So I put some work in, I can see the kinetic energy increase, I can see the potential energy increase, I might see both of them increase. I take some energy out, I can see either the potential energy decrease, the kinetic energy decrease, or both decrease. But the idea is, I do work on the system, which means I either put energy in or take energy out. Alright, now let's see it mathematically. Here's the equation that we find very often. To understand what this is saying, let's look at the right-hand side first. This is the total energy content of my system at the end of the time that I care about it, right? My potential energy final plus kinetic energy final. That's all I've got, right? That's all the energy I have available, is whatever is locked up in potential and whatever is locked up in kinetic at the end of this time. Now, that energy content had to come from somewhere. So where did it come from? Well, whatever that is has to be the amount of energy I had in the system at the beginning, plus however much energy went into or out of my system. Right? So that's this WNC term, the work due to non-conservative forces. Those are the forces that are going to put energy into or take energy out of my system. Notice this is positive, right? I've got a plus sign here. I'm adding the work due to non-conservative forces. Excuse me. But remember, that work itself could be negative. So I could be adding a negative, which would represent energy leaving the system. If that work is positive, that represents energy going into the system. Classic example of a negative work due to a non-conservative force is friction of something that's sliding. That will always take energy out of the system, and it's going to be negative. And that negative comes from the fact that the force acts in a different direction than the velocity. That's where the negative sign originates mathematically. We interpret it in energy as energy going out of a system. For positive work, it could be something as simple as speeding up, hitting something to speeding up. Hitting something to speed it up. In that case, you're putting energy into the system, and that will appear as positive work due to a non-conservative force. But if this is what you stop with, this potential plus kinetic final, that has to be what you started with plus whatever you did to the system to move energy in or out. I hope this clears some things up.